now I will go to the last lecture of week 7. So, I will recap what we did during this week, okay, and then do some practice problems. So, this will complete this discussion on voids, defects, coordination number, and dislocations and so on. Okay. So, week 7 lecture 5, review of week 7 and practice problems. So, let us first review what we learnt. We basically overall we learnt about coordination number and defects. So, initially we learnt about the coordination number, packing fraction and voids in crystals. Then we learnt about defects in crystals such as vacancies, interstitials, impurities, F centers, these are the point defects. Then line defects such as dislocations, disclinations, planar defects, grain boundaries, tracking faults, a little bit about bulk defects like voids and precipitates, and then we studied the thermodynamics of defects, the number of Schottky and Frenkel defects. So, I will do a few problems, fairly straightforward problems. So, the first problem is asks you what is the coordination number of cesium and chloride ions in CSCl, and it is said that the CSCl structure can be visualized as one of the ions occupying the corners of a cube and the other occupying the body center. So, the cesium chloride structure I will just write. So, if you put one set of ions at the corners of a cube, which I will show in blue, and the other is occupying the body center, which is at a height of z equal to half. And this is z equal to 0. Okay, so this is the cesium chloride structure, and now you can see that along with this z equal to 0, there will also be a similar 4 plane of these 4 green atoms at z equal to 1. Okay. And if you look at this this blue point at z equal to half, the blue atom or the blue ion, okay, now that is equidistant from these 4 green ions, and it is also equidistant from the 4 green ions at z equal to 1. Okay. So, clearly the coordination number is equal to 8. I meant was this color. Yeah, the coordination number of these ions is equal to 8. Okay. And now you just by extending this structure, so suppose I just extend it here, now if I shift my plane to z equal to half, if I shift the screen to z equal to half, then you can see that what you have here is exactly equivalent to what you had here shifted by half and the shifting of the 2 ions. Okay, so what I want to say is that this green ion is equidistant from these 4 blue ions, and it will be equidistant from 4 more blue ions located at z equal to minus half. Okay. So, the coordination number of the green ions is equal to 8. Okay. Now, this completes this problem. I just want to make a little observation. We have defined the coordination number as the number of nearest neighbors, and notice that for the blue ions, okay, which could be cesium or chloride, the nearest neighbors are the green ions, and for the green ions the nearest neighbors are the blue ions. Okay. So, the number of closest ions of the opposite kind is 8 in both cases. Okay. You could also ask questions about the number of closest ions of the same type. Okay. and that would be a different answer, and you can easily work that out also. Okay, so next I'll go to a different problem. Okay, this is on the, this has to do with the thermodynamics of defects. The statement is the enthalpy of Schottky defect formation in NaCl is 2.30 electron volts, and that of Frenkel defects in AgCl is 1.60 electron volts. In each of these two cases, what is the ratio of the fraction of defected sites at 1000 K to that at 300 K? Okay. So we recall this, both these are they have two ions. Okay, these are ionic compounds. Okay, with two different ions. So you have sodium chloride and silver chloride. Okay, and in both these cases we saw that we could write the fraction of defects using this as e to the minus delta H by 2 RT times e to the minus delta S by 2R. Okay, that was the expression. Now let me call this FD. F stands for fraction. I'll just use this notation just to make. Okay. Now what we have to calculate is FD at 1000 Kelvin divided by Ft at 300 Kelvin. Okay. So this ratio is so what you have to do is you have to take e to the minus delta H by 2R into 1000 times e to the minus delta S by 2R divided by e to the minus delta H by 2R into 300 times e to the minus delta S by 2R. Okay. So as usual we assume that delta H and delta S do not change with temperature, okay, which is a fairly good approximation. Okay. And so what you can see is that this term will cancel on both sides. Okay. And I can write this ratio as in the following form. I can write this, I can take this up to the numerator and make this a plus sign. So we will have e to the minus delta H, and then I take minus delta H by 2R common. Okay. And I have, well, I'll make it a plus delta H by 2R, then I have 1 over 300 that comes from the denominator and minus 1 over 1000. Okay, so we'll use this is the expression that we'll use. So the fraction of defects at 1000 Kelvin to the fraction of defects at 300 Kelvin, okay, is given by this expression. Okay, and now let's let's by 2. Now there are a few things that you have to keep in mind. This is written in terms of R. Okay, when you write delta H in per mole, okay, delta H has to be written in per mole because this is written in terms of the gas constant. Okay, so then you use gas constant R. Okay. When you use when you give delta H per defect, so it is per mole of defects. If you give per individual defect, then you should use Boltzmann constant. Kb. Okay. So, this is an important thing to keep in mind, and you should always check. Now here the energy is given in electron volts, the defect formation energy is given in electron volts. Okay. So, 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. Okay. So, clearly it is given in this corresponds to the formation of one single defect. Okay. So, this is the formation of one single defect is 1.60. So you have to use Boltzmann constant. Okay. So, that means you have to use Boltzmann constant. Now, let us calculate this ratio. Let us calculate delta H divided by 2 Kb, okay. This ratio. Okay. But yeah, so before that let me just emphasize that if you want to calculate Fd at 1000 Kelvin divided by Fd at 300 Kelvin, then you should use e to the delta H by 2 Kb, okay. And you had this factor of 1 over 300 minus 1 over 1000. 1 over 300 is 0.003333, and 1 over 1000 is 0.001. So, this difference is 0.00233, okay. Well, this is 0.023. So let me calculate this delta H by 2 Kb. This is for Schottky defects. .30 electron volts into 1.6 into 10 raised to minus 19 joule per electron volt divided by 2 into 1.38 into 10 raised to minus 23. This is the value of the Boltzmann constant, joule per Kelvin, okay. And so delta H by 2 Kb will have units of Kelvin, okay, and this works out to that is the unit of this, okay. And if you substitute in that expression, you will get this Fd at 1000 Kelvin this comes out to so this 13333 into 0.0023, okay. So that gives you e raised to 31, okay, which is 3.24 into 10 power 13, okay. So you can see that if you go to 1000 Kelvin, the fraction of the number of defects is much larger than what you have at 300 Kelvin, okay. But actually this 2.30 electron volt is a fairly large energy. So at 300 Kelvin you do not have too many defects in the first place. However, if you go to 1000 K, then you have enormously, you have 10 raised to 13 times as many defects as you had at 300 Kelvin. Okay. Now for Frankel defect, in AGCL, you have delta H by 2 kb. Okay, now in this case this 2.30 in 2.30 in this expression is replaced by 1.60, and if you do that, then this number comes out to, you can work out that number. If you work out this number, it comes to about 9275 Kelvin. Okay, and now the fraction FD at 1000 Kelvin to FD at 300 Kelvin is about e to the 21.6, which is 2.5 into 10 power 9. Okay. Again there is a large increase in the number of defects with temperature. Okay. Now next we'll do another problem. Okay, this is to calculate the radius of tetrahedral and octahedral voids in a perfect FCC's lattice of side A. Okay, I'll write this in A, the script A. Okay, so A is the size of this lattice, and you have to calculate the radius of tetrahedral and octahedral voids. Okay, now to do this, you have to, okay, again let's recall a few things about the FCC lattice. Okay, so in an FCC lattice, or the center atom is in contact with each of the 4 corner atoms. Okay, so the atom at the center, at the face center, is in contact with each of the 4 corner atoms. Okay, but the corner atoms are not touching each other. So this is what an F. I think this came a little big. Let's make it smaller. Okay. So this is what it looks like in one plane. Okay. So the face center atoms is in contact with the corner atom. Okay, but the atoms at 2 adjacent corners do not touch each other. Okay, and now you recall the tetrahedral void, okay, is located right here at z equal to 1 by 4. So that is the location of the tetrahedral void. So the coordinate is x equal to 1 by 4, y equal to 1 by 4, z equal to 1 by 4. So this is the tetrahedral void location. So you can ask, what is the distance of the tetrahedral void? So along this, let me call this O A. A is the location of the void, and along this OA direction, O A direction. Okay. So now this length of OA is equal to, so that is the coordinate of A well, okay, so I'll write it in the following way. So you can look at the coordinates of A. Coordinates of A are 1 by 4, 1 by 4, 1 by 4. So this will be 1 by 4 square plus 1 by 4 square plus 1 by 4 square. Okay, and O is 0, 0, 0. So you keep in mind that O is at 0, 0, 0, and the coordinate of A is 1 by 4, 1 by 4, 1 by 4. It doesn't matter which way you see, but basically the distance and this whole thing's under the root sign. So, this is the length of OA. So, therefore, length of OA is equal to 1 by 4 root 3. Okay. And now along OA, what you have is you have this one atom, one face center atom, okay, and so this is the radius of the face center atom. Okay. Now, so clearly the tetrahedral void, if it is sitting at A, then the radius of the tetrahedral void clearly you have the relation radius of this face center atom plus the radius of void atom equal to A root 3 by 4. Okay. And so this implies that the radius of the void is equal to A root 3 by 4 minus radius of the atom. Okay. Now, the radius of the atom can be related to A. Okay, A is this side. Okay. So, the radius of the atom can be related to A, okay, because as we said, along the face center they touch each other. Okay. So, clearly this from O to this point B, okay, so this length is equal to is 4 times the radius. So, so we can say that the 4 times radius is equal to OB is equal to A root 2. Therefore, R is equal to A root 2 by 4. Okay. So, then the radius of the void is equal to A by 4 root 3 minus A by 4 root 2. Okay. And so, root 3 is 1.73, this is 1.41, okay, and you have a divided by 4. Okay. So, this works out to about 0.079 times A, and equivalently you can also see that since R equal to A root 2 by 4, okay, I can just divide by A root 2 by 4, okay, and multiply by R. So, I can write this as 0.079 divided by A root 2 by 4 and into R, okay, into A into R. Okay. So, I just multiplied and divided by R, okay, and what will happen in this case is that the A will cancel and you will get, so you will get this as basically 0.22 R. Okay. So, in other words, the radius of the tetrahedral void is about 22% that of the ion. So, the size of the tetrahedral void is about 22% that of the ion. Okay. What about the octahedral void in FCC? Now, the octahedral void is at the center of the cube. Okay. So, now if you go again, take the, let's go back to the planar view. So, so the octahedral void is located right at the center of the cube. Okay. And now if you go from this point at from the center at so the center of the cube is located at z equal to half, x equal to half, y equal to half. Okay. And if you just go along this line, starting from the face center that is in the plane of the screen to the center of the cube, which is located at z equal to half. So, along that line if we go, then you will get the relation for the octahedral void. So, So again just to clarify, what I mean is that if you take this point that is in the plane of the screen, and then you come directly up along this to z equal to half. Okay. So so then along that line, okay, or maybe I'll show it in a slightly different way. Okay, so I'm going from the center of this face. I'm going from the center of this face to the center of the cube. Okay, so so clearly this distance that I've traveled is a by 2. Okay, and so along that line you can clearly see that a by 2 should be equal to the radius of the void plus the radius of the atom. Okay. So clearly for the tetrahedral void, RV plus R is equal to a by 2. So RV equal to a by 2, and now we use the expression for R minus a root 2 by 4, and this works out to about 0.158. So it's actually nearly twice that of the tetrahedral void. Okay, and you can also work it out. It comes out to about 0.43 R. So with fairly simple coordinate geometry, you are able to calculate the radius of each of these voids. You have to visualize these things. Okay, so it initially takes time, but after some time it will become very easy. So with this, I will conclude week 7 of this course. Some of the lectures have been quite long in this week. Okay, but part of it is because it takes a little while to draw and explain those structures. Okay, but otherwise the content for this week is not that difficult. So I will conclude this lecture, and we'll start the 8th week after this. Thank you.